In this video, we'll be talking about long division and the division algorithm. Most students are introduced to long division of numbers around 3rd or 4th grade. That's here in the US at least. They're later introduced to long division of polynomials. That's around 7th, 8th grade or early high school. The important thing to realize here, though, is that both processes are essentially the same, though. So maybe you've never thought about this, but for instance, if we want to divide 67 by 4, we have here that 67 divided by 4 is what? Well, you try to match the 6, right, with the 4. And if you can't match that first number, then you move on to the second, right, and try to match it as a whole. Well, we can match 4 into 6, and the closest we can get is by multiplying it by 1. 1 times 4 is 4. 6 minus 4 is 2. Then we say, okay, well then 4 can't go into 2, so we bring down the 7. Now we want to match 27. The closest we can get is up to, without going over, is 24. That would be 6 times 4, so we have 24. Change the sign. That goes away, but we have 7 minus 4, which is 3, right? And so we have a remainder, right? Namely, what we write here is, we say, well, that is, we have that 67 divided by 4 equals 16, but then we also have a remainder of 3 over 4, right? So here, in other words, what we have here is this and this are the same. And this is our dividend. It's the thing we divide that we are dividing. Here we have our divisor. I guess technically here as well, divisor. Then we have our quotient. And we have our remainder, right? Remainder. Okay, so I use these terms a lot when it's nice to have terminology, right? But the most important thing is that we can learn a lot about this and proceed to repeat the same thing with polynomials. That is, to do this division, we write out x squared plus 3x plus 5. And we're going to divide it by x plus 1. Well, again, we want to match this term by multiplying this term by something. Well, here we need to at least multiply it by an x. So x times x plus 1 gives me x squared plus 1. But then I need to change all the signs just as I did here. Of course, here with polynomials, I have to change everything because I'm distributing through the sign. So here, and that's times 1 times x. Here, those should cancel. We get positive 3x minus 1x is 2x. Well, now, bring down the next term and move on, right? I'm trying to match 2x by multiplying x plus 1 by something. Well, I can match it by multiplying by 2. So I get 2x plus 2. Again, I have to change all the signs, though. Doing that, I end up with a 3 there, and those cancel. So again, this is my... Again, I can write this the following way. I can say that x squared plus, I can say that this whole thing, let's just write it that way, save some time, is really equal to what? Well, here I have that this is, it equals x plus 2 plus 3 over x plus 1, right? Where again, this would be my dividend. Dividend and divisor. This would be my quotient. And this would be my remainder. Right? But the most important thing in all of this is that this actually allows us to factor. So first, let's put that on hold, though, and look at the division algorithm, which kind of says this in general. Namely, if f of x and d of x are polynomials such that d of x does not equal 0 and the degree of d of x is less than or equal to the degree of f of x, then there exists unique polynomials q of x and r of x such that f of x equals dx times q of x plus r of x, where r of x equals 0, or the degree of r of x is less than the degree of d of x. In other words, what are we really saying here? Well, here you really want to think of f of x as your dividend and d of x as your divisor and q of x as your quotient, which is why we use q, and r of x as your remainder, right? All right. But equivalently, what we're really saying here is if you divided the whole expression in the last page by d of x, we would get exactly what we saw here. Here, we say f of x divided by d of x, since we know f of x has to have a greater degree, a greater than or equal to degree to d of x, that it is improper. Whereas the fraction r of x over d of x is actually proper, as its degree, the degree of r of x, as we saw on the last page, must be less than the degree of d of x, assuming r of x isn't 0. An interesting question to ask yourself is, what if r of x actually is 0? Well, we'll see that happen in a minute through these examples. So let's go ahead and look at this example first. Using long division here, we'll have that. So it's important to write out all your terms, otherwise things will get messed up. So 0x squared plus 0x minus 1. And put x minus 1 into there, okay? Here, again, we want to match the terms, so we have x squared, we'll get that up to an x cubed, minus x squared. But then we swap all the signs. That goes away, and we have x squared plus 0x. Well, now we want to match x squared. To match x squared, we multiply by x. We end up with x squared minus x, but then we change all of our signs. That cancels, and we get a positive x. Then we get x minus 1. Well, to match x minus 1, we just add 1, right? So we get that, change all our signs, and everything cancels. So we have a remainder of 0. In other words, what we have here is x cubed minus 1 over x minus 1 is the same thing as just x squared plus x plus 1. Or equivalently, what we're really doing here, the way to think about this is we're really factoring out x minus 1. Well, we'll talk about that momentarily. But for now, that's really what a remainder means, is we can factor out x minus 1. Let's go ahead and look at this example, though, first. So with this example, again, we're careful and we write out all of our terms. We write out the polynomial in standard form with all of its terms included, okay? Here we have 1 plus 3x. So let's write that as 3x plus 1. That's going to be our divisor. And our dividend is 6x to the 4th minus x cubed minus x squared plus 9x minus 3. So again, I'm writing that in standard form, which means that I have all the powers in descending order, starting with the highest power. Here, I want to match 6x to the 4th with 3x, so let's multiply by a 2x cubed. This power and this power should match, otherwise you're doing things wrong, right? So we get 6x to the 4th plus 2x cubed. But then we change all of our signs. That will cancel. We get negative 3x cubed minus x squared. Well, now to match that, we need a negative x squared plugged in, right? Negative x squared plugged into that will give me what? That'll be negative... To match that term, I need a negative x squared, so minus x squared. When I do that, I get negative 3x cubed minus x squared, but then I change all the signs and everything cancels. Neat. Here, I bring down the 9x, but then I need to also bring down the negative 3 because I won't be able to have all my terms accounted for. If I do that, I end up with 3x plus 1. Yeah, so to get that, let's multiply by 3. So we have a 0 there, but plus 3. When we do that, we will get 9x plus 3. But then we change all of our signs, so we get a negative 6 here as a remainder. In other words, this is really equal to 2x cubed minus x squared plus 3 minus, we'll go ahead and bring the minus to the front, minus 6 over 3x plus 1. Okay. So now it's time for you to try an example. Go ahead and use long division to divide and check the result for each of these. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we see this one is pretty straightforward because you have a remainder of 0, so you just get that. This one isn't as straightforward. One, you have more terms here, but it works basically the same way. You go through and you get this as your remainder, this as your quotient. So you write out your quotient. Then you put your remainder on top of your remainder on top of the divisor, which is that. And so, but what I did is I went ahead and factored out the negative so I could put it in the front. But then to do that, you really need to put the negative there because you got to factor out both terms. But the big point, as I've mentioned a few times in passing so far during this video, is that if the remainder is 0, then d of x divides evenly into f of x, meaning we can actually factor out d of x out of f of x to get our quotient q of x. What does all that mean in practice? Well, if we go through and we divide this polynomial out, 6x cubed minus 19x squared plus 16x minus 4, and we divide that by x minus 2, well, we go through our little algorithm here, right? We have x minus 2. We got to figure out how many times that fits into there. That's going to be what? 6x squared times. So we get 6x cubed, remembering to reverse the signs as I go, plus 12x squared. Those cancel. I have negative 7x squared. So now plus 16x. I need to match that term. How will I do that? We'll multiply by negative 7x. I will have positive 7x squared, changing signs, minus 2 times that's 14x. So I have 2x minus 4. Let's multiply by, what should I multiply by? I should multiply to match that I need plus 2. So I get 2x plus 4. Everything cancels. I get 0. That is what I actually have here is that I can factor out this. So what I've written, one way to think about this is 6x cubed minus 19x squared plus 16x minus 4 divided by x minus 2 actually equals 6x squared minus 7x plus 2. But the better way to think about this is if you multiply both sides by x minus 2, what you're really doing is you're factoring out an x minus 2 out of that. So 6x cubed minus 19x squared plus 16x minus 4 is actually equal to x minus 2 times 6x squared minus 7x plus 2. So now it's time to have you try an example. So go ahead and do the following division that's given and use the result as I did to factor the polynomial actually completely. Okay, so you'll need to go a little bit further. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we see that I go ahead and I do my division. I end up with this as my answer, but then I see I can multiply both sides by x plus 4 to get to here. But what then I can do is, since I already have this partially factored, I can factor this term the rest of the way because it's a difference of squares, right? That's 3x squared, 3x quantity squared minus 7 squared. So factoring the difference of squares, I end up with this as the total factorization. For more practice in doing long division, be sure to see page 142, and work problems 1 through 3, 7a, and 11 through 24. And in our next video, we'll talk about synthetic division.